We are going on record. Thank you for finding it possible to join this meeting. And we are continuing our class in computational chemistry. We have completed half or even a little more than half of the class. Because of our democratic procedure, we do not have much of exams, but you do have a form of feedback as presentations, and they are counted like this major contribution to your grade, which should be counted like midterm. So when we meet next time on Thursday, please consider to present your presentations. And in order to have it quick, it would be great if you send the PowerPoints before midnight on Wednesday, so that we can I can upload them on the same computer, so that we save time on loading them to the computer, so that when you come up to the stage, it is ready. We will try to have this set up so that we do not switch cameras and everything will go smoothly, and we spend less time on technical issues. And with Thursday meeting, we will complete the Hartree-Fock session based on wave function methods for electronic structure. So who we are and what we are doing. We are picking up skills and theories to computationally characterize properties of materials. And we did split nuclear and electronic degrees of freedom. Now we have our nuclear degrees of freedom frozen, and for electronic degrees of freedom, we went through the so-called Hartree-Fock theory, which allows to reduce multi-electron problem into efficient one-electron problem, with specific tricks to take into account the background field created by the all but one electrons. And this theory is solved through so-called self-consistent iteration procedure. By developing this theory, we got acquainted with the concept of molecular orbitals, which are nice to visualize and look through. And we briefly went through possible observables, where we touched the Koopman theorem, where in approximate way one can assign reasonable scientific value to energies of individual molecular orbitals for comparison with experiment. Do I miss something valuable to summarize? And we do have night sessions on practical skills, which you will cover in your presentations. So how to implement the theory and apply it to practical molecules. If one day some of us should not visit the lecture and just sit home and push this number and see if the streaming will come through. It's still a puzzle for me. So, what are the what are we doing today? Is it right that I have to collect some pieces of paper? Okay. I'm not giving anything in return today, but probably to make you feel better make it feel better, we can do what? We can agree that there will be no homework on coming weekend. Yeah. Because you are committing a lot of hard work on the night from Wednesday to Thursday. Aha. So you contributed the density metrics to the procedure. That's good. But not if you implemented equations. Noticeable percentage skipped equations. But the main idea is writing words of everyone. So it will be our last effort on the Hartree-Fock theory on Thursday, but starting from now, we are departing from Hartree-Fock theory. Why? What is wrong with it? Anything you didn't like about your computed results? I'm just playing with the cameras. So, anything you didn't like in practical results when you were modeling some realistic molecules? Any observations? Yes.
For one molecule, the script decided that the last orbital, the last unoccupied orbital, the highest energy, yeah, that was the band gap.
Too high.
Yeah, it picked here, should have been here.
Exactly. So the Seth is correct. So the general Hartree-Fock is good theory because it shows rigorous way to solve complicated problems in a reasonably quick way. But it does misses some factors that make results consistently overestimating band gap. So whatever has red color will be shown as blue. Whatever is blue will be ultraviolet. So it is consistently increasing the band gap. And the short answer is that it does miss so-called correlation energy. So all electrons are considered equal, and there is no effect of hide-and-seek game. When in reality, the space occupied by one electron with a certain spin cannot be occupied by another one, and therefore, if you contribute another electron, it will avoid this space. While in Hartree-Fock theory, everything is smeared out, and this hide-and-seek is kind of skipped. So this is a correlation effect, associated correlation energy, and therefore the total band gaps are overestimated. Second reason to depart from Hartree-Fock. Many people who call themselves computational chemists do not want to depart from Hartree-Fock, and instead they build improvements, incremental improvements to the Hartree-Fock, looking to a higher level of interaction between electrons. So those, for example, perturbation theory, MP2, if you were scrolling to menus of the methods, whoever is presenting it, you will see that there are several methods that are based on Hartree-Fock, based on wave functions. But they all, especially if you go to incremental increase of precision, they will be too expensive computationally. The Hartree-Fock method rests on explicit evaluation of two electron integrals. And there are procedures that cannot be simplified. On the contrast, there is a completely new, completely different branch of theories that are considered a trick. They are not considered first principle theories by some pure quantum chemists, because there are very serious approximations in the very seed of those theories. And I'm going to density functional theory. So, but developing from this seed, one can get an ultimate efficiency, ultimate cost, numerical cost to precision ratio, and one get very acceptable level of precision with moderate numerical cost. This branch of theories are predominantly imprecise. There are some strong approximations, but they work so nicely that it is worth of spending like a month to learn them. And 90% of computational chemistry calculations and publications are based on this theory. So it is not a bad idea to spend time on it. So for about a month, we will be looking at principles behind this theory, and we will accumulate practical skills in running density functional theory for different models and different pieces of software. It is already included in Gaussian that we are working on, but there are another different pieces of software that also implement this theory. And here is a brief overview where we are. So we need to complete presentations, and we are already to the chapter to the density functional theory. Today it will be more or less easy start, so that you do not need to come with your full concentration and full capacity, but when we meet on next Tuesday, this will be maybe third hardest. Our first hardest was Born-Oppenheimer, second hardest was exchange energy, and third hardest will be theorems. So this theory is based on theorems that look a little counterintuitive. It is not much of mathematical derivations, but it is like twisting your brains and looking from completely different angle. And then we will borrow the same intellectual baggage that we already have, the idea of self-consistent procedure, and when we finish this chapter, we will set up flowchart that is running when the DFT algorithm is being computed in the software, and then we will go over additional details, and somewhere we should stick observables based on density functional theory. So here is just a little reminder of what we will be doing on in 2 days. I hope everyone is happy. Everyone's wish is taken into account. If you are completely unhappy, if you want to modify something, come to me right after this meeting. So we will try to spend plan on 3 minutes presentations, but they will run for seven minutes anyway. It's just a nature observation. And in about 3 weeks from now, we will do similar things about another piece of software. Okay. An easy start. The goal of electronic structure part of computational chemistry, when we removed the nuclear degrees of freedom, is to find one point on potential energy surface. Find the total energy for given set of positions, right? And we were able to generate it based on wave functions, Slater determinant, molecular orbitals. We found total energy. We have the same goal, to find total energy. But instead of wave function and wave functions, we will use the concept of charge density. So there are two very simple concepts that we need to get acquainted with and comfortable with. So one is charge density, which is just electronic clouds. And second is concept of function. As soon as we accept them and we agree that they can be connected to the total energy, we have the basic principle of density functional theory. And it is simplified plan. We'll go through definitions and some background theory, then there will be theorems, algorithm, and observables. And then we are done with this density functional theory. Camera. Okay. So what is density?
That's what we want.
Yes, that's correct. So mass over what else?
Density of what in that case? We can
Yes.
change that eventually.
So we will be dealing with density of electrons. That is a replacement of orbitals and wave functions. In our previous life, no, not in the eternal way, just in the meeting of a couple of weeks ago. We had a sequence of molecular orbitals and multi-electron wave function. So instead of these two concepts, we will go to the concepts of charge density. So if we do have molecular orbital, we can take it conjugated at the same point of space, same orbital, and tell that this will be absolute value squared. It will be probability to find, well, if the electron accepts to reside on this molecular orbital, then it will be found in the given space with this probability. Maybe times volume. But there is an alternative interpretation of quantum mechanics. That orbital is occupied by one electron. But electron is a wave. It is divisible. We should put it on record. So there is if we have so many, and let's use the letter rho, in the vicinity of position R, it means that like 1.5% of electron is placed in this little area of space. So it is distribution of one electron density if it resides on a given molecular orbit. So it is yet acceptable, but we are starting to screw our brain. So common interpretation that wave functions correspond to probability, but we start thinking that it is density of charge of electron. suppose that our molecular orbitals are good orbitals. What should we write here? Wave function conjugated multiply, or one electron orbital conjugated multiply itself and integrate over the whole space. One. Yes, because it is normalized. Good function. Okay, so we rewrite rho sub I r equals 1. No objections. I will come to this point in a second. Now let's think about the second word that we need to accept. What is function? I would say it is something similar to function, just with AL at the end.
A function that is dependent on a function.
Function is dependent on a function. Yes. So how can we interpret it? Function that is dependent on a function. What is a function?
For one input, you get one specific
Yes,
output.
yes. So function, it means that if you have x1, x2, xn, we have values for each argument. We have specific value of function. Good? So f equals f of x, round brackets. So we had a prompt, function of function. So it means that here we establish correspondence from one number to another one. And if we do have n set of numbers, and it will correspond to one value. Then we have f prime f. It will be another value. So for each set of numbers, we accumulate it into one number. So one function continues, many numbers, is accumulated into one. What are examples? Like any, for example, any integration. Integral of x dx equals with limits. Will be a number, right? Without argument. So we are going from a function to a number. This is a functional. And typically one writes g equals g of f. Rectangular. Square brackets. Square brackets. We have almost accepted density functional theory. We know what is density, we know what is function. We are very close. Now, suppose that we consider a molecule is more than one electron. And we set up summation of density for electron for the first orbital, density of electron for the second orbital, up to the highest occupied molecular orbital. Argument is the same everywhere. So it will be summation of electronic clouds associated with molecular orbitals. And if you add all of them together, we can consider it as a total density. We are skimming through. It is not rigorous, although very close to being correct. What if we place integration? To the left and to the right part. Any ideas what will be the answer? Huh? There is no provocation, there is no challenge. It is simple. So by integrating each orbital, each density for each orbital, we get one. Right?
So we get S.
1, 1, 1, plus 1, plus 1, plus 1. How many times?
Number one.
As many times as many orbitals we have, or as many electrons, occupied electrons. So we can say it's whole, or it is number of electrons. Number of electrons. So now we can write the number of electrons is a function of the total density. Make sense? No big counterintuitive steps? Good. So number of electrons depends on density. It is a little silly because if you consider the model, we know what the number of electrons. It is kind of input. And it is, we can count electrons without generating the total density, but it just shows the logical connections. And the goal of density functional theory is to establish total energy as a functional of total density. So if we find this functional, if you find a way how to make correspondence from the distribution of electron density in space to the total energy, we have this task completed. Questions? Objections? Okay. Density is with orbital conjugated times itself. Integration of density over all space is 1. If we add together all densities corresponding to molecular orbit, all occupied molecular orbitals, we can integrate total density and get norm 1 from each orbital. Therefore, it will be total number of electrons. So, total number of electrons is a function of the total density. And our goal is to make the same trick for the total energy. We will spend about 4 or 5 meetings to get it, because it's a little more challenging than number of electrons. How are we doing? Do you have steam to go over one subject more? Good. So let me write down the answer right away, because otherwise there will be not much of motivation. So in one of the oversimplified theories, one can solve this problem and get the total energy as function of the total density. This will be not big help in describing molecules and realistic materials. It will be very similar to spherical force in a vacuum. But there is one theory where one can, in 20 minutes, derive total energy as function of density. We are making it only for encouraging ourselves and believing that it is possible. So the name of this theory is Thomas Fermi. We know that the first name of the Fermi was Enrico, so it is not a first and last name. There are two different persons. Thomas Fermi theory. So this is not a critical, what follows is not a critical information for the course. If you are tired or busy, you can lean back and take a nap. The main message is that total energy can be expressed in terms of total density or specific approximations. If you accept this message, you're done for the day. If you're curious, you can follow how it can be done and what are the approximations. In practical life, everything will be much more complicated. It will be just a little sketch that we do not have fear of the unknown field. So we will achieve this goal in 8 steps. And the steps, this panel will be always on the left side, so we can watch the progress. Like if you lose the track of narration, or one part of derivation is more boring than another one, you can always pick up and say, oh, okay, we have so many % towards completion. The idea of this Thomas Fermi theory rests on several cornerstones. First is that electrons have suddenly forgotten that they need to interact with each other. So it is a universe where electrons do not interact with each other. Who you are? No, I do not know you. I come through you. Non-interacting electrons. Otherwise, such simple derivation will not be possible. What else? It is a universe that contains of electrons only. So there are no ions. Just empty space with ignorant electrons that do not know that do not recognize each other. So it's a free electron gas, non-interacting electrons. Universe of these silly electrons. You like it, right? Now, what else? It's not the whole story. No. We all like freedom, and we do not like prisons. Genuinely. But these electrons are placed into cells. So the whole space is splitted on the little jail cells, little boxes, and electrons are distributed over these boxes. Although they do not interact with another electrons, and there are no ions. So if you take it as an input, as an output, we will get this answer. So total energy is integral of total density into power 5/3. boxes. If I show everything on the slides, it will be probably boring. I should scratch something. Preset number 5. So we divide all space onto equal boxes. Generally, size of the box can be rectangular, but we assume that they're cubes. And we agree that so many electrons is residing in one cube. And the volume of one cube is L to the power 3. Then we can introduce density. Density mass divided by volume. And we don't care about mass. We care about charge. So density of charge.
Why are you using change in? Why are you using delta n and delta n?
Because total number of electrons in this fairy tales universe will be n capital. Delta n plus delta n plus delta n into summation over all cells. Good? Nothing counterintuitive. Now, we need to tell something about energy of electrons that are residing inside one cube. So, an electron is a particle. This L3 cube is a box. So we need to recall particle in the box. Logical? Good. So what is an energy of particle in the box? H bar square n square k square 2m. That's it?
N squared over L cubed, that's no L.
Well, let's do careful. I can make little errors, but then I can tweak the video and skip.
Squares. If A is 1, then
So let's be careful. We know for sure that P squared over 2m is kinetic energy. And since those are silly electrons, they do not interact with each other, there is no potential energy, only kinetic energy. Now, what is momentum? Momentum minus IH bar ddx, or minus IH bar k over 2L, where k is number of nodes, so there will be states with 1, 2, 3, and more nodes, and the energy is quantized. So it will be h bar squared 2m, and now we will have 4l squared
a squared, so h bar squared 8 m l squared times kx squared. So it is for one-dimensional box. Make sense? We do not see errors. Maybe I do not need to edit video. Our boxes are three-dimensional. So the energy will be x, y, z components. A bar square 8 m l square and kx squared ky squared kz squared. So three quantum numbers, that's ky, kz, determine energy of a given electron inside the box. So we can depart from Cartesian space and go into space of quantum numbers. It's also three-dimensional, and we can call it like radius. So it is, I don't know how to define it, average quantum number. Square root of k squared k y squared k z squared. Average quantum number. Then energy of one electron is e plus bar square e m squared r What is our goal and what are we doing? Are we just having fun of looking at the particles in the boxes? No. We need to find energy. That's what we call the goal. Find energy of all electrons inside the box. So there will be more than one electron. How do we approach this goal? And how many electrons is inside the box? How many? So we keep this one, and we answer about the number of electrons inside the box. There is no chance to build everything based on declared approximations. We need to have one more input. And this input is connected to the name of Fermi. Is what is it? It will be very pleasant and easy to assume that this equation belongs to the pool of common knowledge that we can depart from. So suppose anyone wants to comment, or you give this opportunity to me. So if you do have a molecule, or even an atom, you do have the Aufbau Principle. You fill it with electrons starting with lowest until you get rid of all electrons in your all surplus electrons due to Pauli exclusion. And if one projects this concept onto systems with very high number of electrons and very dense orbitals, then this concept of orbitals being occupied, and then empty, is translated into the language of Fermi distribution. Fermi distribution. Does it click any bells? Or not yet? So this is a function of how the number of electrons depend on energy of orbital. Electrons as function of orbitals. Let's do it on this board.
He's getting good.
Well, it is what I'm learning. Let's make a little surgery to this function. F1 divided E minus E. ET. What is KT? Yes. So, surgery. E to the power minus E minus EF ET. How does it look like? So at the point when argument of exponential is 0, the value of exponential equals 1. When we go to the increment of the argument of exponential, it increases. When we go to the decrement of argument of exponential, it decreases. So here it goes to 0, here it goes to infinity, right? What if we add 1? Addition of 1 means that we redefine the y-axis. So where we had 0, now we have 1. Where we had 1, now we have 2. And where we had minus 1, now it is 0. Okay? So now this function tends to 1 at infinity, and it still tends to infinity at minus infinity. Now let's continue our surgery of the function. what if we practice 1 divided by everything we have here?
Left side will be -2 -1. Sorry.
Yeah, the left side should
And
go
right side
from
will go to
0
infinity.
to 1/2.
So if epsilon goes to plus infinity, we have 1 divided by 1. So function will approach 1. Agree? If energy goes to minus infinity, we have 1 divided by infinity. 0. If we have E equals E Fermi, 1 divided by 2, 1/2. And then we continuously connect these points. And for pleasure, for convenience, let's put plus sign here, which means that we are looking into different direction. Okay? So how would this function respond to the value of kt? If kt approaches 0, the function will be very sharp. If kt grows, it will be more shallow. So it may sound boring, but at least logical. You do not find deficiencies. So I am flipping it by 90 degrees. So here is f of epsilon, and here is energy, and here is E f 1, 0. And suppose that temperature equals 0, which means that it will be very sharp. And instead of continuous function, I will be showing just points. Number of electrons on given orbital, if such an orbital exists. So it will show that up to specific energy, which we call E sub Fermi, orbitals will be occupied. All orbitals above will be unoccupied. So it is just mathematical verbalization of our common knowledge that we feel orbitals as much electrons we have at our disposal. And here we introduce Fermi energy. Fermi energy, which is similar to energy of highest occupied orbital, or halfway between highest occupied and highest one. Good. I'm going to switch to this board. So we need to connect together this concept that we can define specific energy of the last occupied orbital, that energies can be defined by quantum numbers, and that we need to bring one more piece into here. So we need to count the degeneracy. I was seeking for this word for 5 years. So we will count for degeneracy, which means how many orbitals do have this energy. Because there is an ambiguity. There are different values of these quantum numbers that generate the same energy. Okay, at least we know whom we are hunting. Degeneracy. When my native English is not my native language is not English.
I could never tell that.
When I just came to the country, I used the help of the secretary at the university where I was for like catching some typos or whatever. And I needed to send an abstract to a scientific conference. I wrote the abstract, brought to her, and she's secretary, not a scientist, just nice lady. And okay, can you look through? Okay, not bad, but here, you know, this is not very polite word. What? And there was the degenerate thing. She said, you know, here we try to be polite to each other, and degenerate, those are like people who are not very developed. Can you find something? But we are not we are talking about degenerate energy states. So here it is a good word. So we keep browsing in the space of quantum numbers. We need two-dimensional space of quantum numbers, but it is too challenging for me to draw. You can imagine that there is another dimension. So I draw only one x and y quantum numbers. And the energy of particle in the box depends on three quantum numbers. The x, the y, and z. And I will be drawing just two of those. So here is ky equal 1 and kx equals 1, 2, 3, and so forth. Here's ky equals 2 and kx equals 1, 2, 3, 4, 5, 6, and so forth. Ky equals 3 and kx equals 1, 2, 3, 4, 5, 6. So it is a space of quantum numbers, of quantum states. And when we need to find who of them are degenerate. So we can identify that several blocks, several sets of these points will correspond to the same energy. And according to this equation, which means same as in analytical geometry, equation for the circle or equation for the sphere. So if we tell that R equals x squared plus y squared plus z squared, it means all points that are offset from the origin by this radius. Right? Here, offset from origin. Offset from origin. Here we do have the same. We have, instead of radius, we do have this energy times constant, And on the other side, we have this quantum numbers. So all states that will be offset from the origin by this much, so this, will be degenerate states. Good? Now we need to go quantitative and count them. I'm not going to count 1, 2, 3, 4. We are going to set up some mathematical equations that we all will believe. So let's count total number of states with energy less than some fixed energy. So let's count what is inside. If it is two-dimensional space, it will be area of a circle. 2D area. Pi r squared. If it is three-dimensional, it will be volume. 4/3 pi r cubed. Right? But right now we are not in our favorite space of comfort. We are not in Cartesian space. We are in this crazy space of quantum numbers. But it's still rectangular, Euclidean space where we can apply same analytical geometry equation. So, number of states that correspond to energy less than E prime will be 4/3 pi r cubed.
And we need to divide by 8.
Yeah. We will add Levi factor. This is correct, but by the end, by the final equation, energy equal integral rho 5/3 dr, we will put all constants into predefined constants. So we are not, even if we screw up with constants, the answer will not depend on it.
In this case, we are in two-dimensional space.
No. Three-dimensional space. There is another axis, kz, and we are looking for
Space.
for a sphere. What if we are looking for all states that stand between E prime and E prime plus D? What if you are looking on all states in the vicinity of a specific radius or specific energy?
Just take away the inner radius from the outer radius.
If you take that we neglect the constants, but formally the volume of the skin is area of the skin times thickness of the skin. So we need to dn over dr times delta r, right? So we take this equation, take derivative over the radius, and then multiply by thickness. So by derivative, we get from volume to the surface area, and here will be the thickness parameter. So So derivative of the third power. X y equals
3x squared.
3x squared. Yes. So Levi's factor. Third from school, high school geometry. Y stays here. 3 from calculus. R and 2 from calculus. Times delta up. Okay. What is it?
I ask.
No. How can we interpret? Too early? Let me add one line more and then ask my question once again. So the question is, what is it? How do you interpret? And I am going to stand on my head. Not physically. I'm going to invert this expression and tell that our R bar equals square root of E times 8m squared divided by A bar squared. And if we are meticulous, we can simplify it by putting L H bar away, square root M, square root energy, square root of T. And let's put square root of energy even apart, times e to the power 1/2. So the radius in this crazy space is a square root of energy with some constants. Now we are going to merge this and this together. So I am planning to rewrite this expression using this definition and then ask you a question what it is, how to interpret it once again. Instead of r squared, place what?
Why did you take the square root?
Hmm?
Why did you take the square root of r squared if you have r squared in front?
Because this is more general. This is connection between our variables that do have meaning. And here is just a silly algebra. So this should be the number of states in this thin shell. This should be the density of states as function of energy. Density of electrons, of this non-interacting electrons in the box that do not interact, and their number can be different. Okay, let's go through the pre-recorded stuff. So we do have so many states. We are looking for the volume, which is proportional to the third power. And here we have the number of states in the shell. Now we make a derivative of this distance and look how many states are in the thin shell. So it will be power 2. And here we convert, establish conversion between energy and this radius. So the number of states, okay, I caught myself on the error, but if you didn't find it, it's good. Here is all correct, and all but last equation, all equations are correct, but they are not leading into right direction. So here is total number of states as function of energy. So constant energy to the 3 over 2. 3 from cube, 2 from the conversion. Now, for finding number of states in the thin shell as function of energy, we should take derivative not over the r but over the energy. It is what we need. And if we do it over the r, one needs to add a second derivative as a chain rule. Good. So, if you take derivative of the total number of states over energy, this will be number of states that have specific energy, density of states. And it will behave as a square root. Make sense? So we are slowly departing from this crazy space of quantum numbers, and now we are trying to establish connection between energy, total energy, and energy of orbitals, and then go to density. Density of states. And if you were exposed to advanced quantum chemistry, you remember for 3-dimensional, 2-dimensional, and 1-dimensional density of states looks different. There's 3-dimensional square root. Now, the last step where it is what we need, the Fermi distribution that we already covered. And now we need to find the total energy of all electrons inside the box. Make sense? No objections. Okay. And we will bring together it was not on the record. We will bring together all components that we have discussed by now. Density of states is constant times E 1/2, right? Occupations is this Fermi distribution. And we need to find total energy of all electrons inside the box. How do we find expectation value of something? It's not science, not physics, not chemistry, it is math. Momentum of a distribution. It is probability to find something times the variable that we need to make average over. So if you need to find expectation value of energy, we put energy, we put density, probability that there are states at such energy, and the keyword is degeneracy, such energy, times number, times occupation of such states as function of energy. So energy, degeneracy or density of states, and here occupation. Integral over all possible energies. Now, we do assume that temperature is equal to 0, and our Fermi distribution reduces to our standard thing with only occupied and unoccupied, which means that we need to integrate only from minus infinity to Fermi energy. So integrate only over occupied orbitals. Then we can remove distribution E times n of E t, right? And this n of E can be replaced by constant times e power 1/2. Constant e power 1/2 and times E dE. Energy of all electrons inside the box e to the power 3 over 2 d. What is the integration of polynomial? The power get increased by 1, and 1 yields a denominator. Energy to the power 542. And we can agree that there are no energies below 0. From 0 to E Fermi. Then total energy inside one box will be constant times energy Fermi to the power 5 over 2. So if you know the energy of HOMO, which is Fermi energy, we take power, and no matter how many orbitals were, we get the total energy. We already got it. But it doesn't make sense to connect energy to energy. We need to connect energy to density. Right? Where is the density? Density is number of electrons per volume. So the total number of electrons in the box will be the same equation, but without the energy. So number, degeneracy times occupation. So degeneracy is e to the power 1/2. And occupation is either 0 or 1. Therefore, we integrate only until Fermi energy, or occupation is 1 to d. And the rest constants. Integration of power 1/2 leads to power e 3/2. And we evaluated from 0 to Fermi energy. So total number of electrons will be constant times Fermi energy to the power 3 halves. Good? Now, let we stand on our heads once again. Invert the dependence. So, if number of electrons depends on energy this way, then we can take delta n to the power 2/3 will be Fermi energy. Right? So now, if we know the density number of electrons, we can find what will be the energy of whole, Fermi energy. And we are going to plug this expression into here. So delta E will be the constants. Now, instead of Fermi energy, we plug in delta n to the power 2 volts to the power 5 volt. Good. Can we cancel the powers this way? What is wrong? So delta E equals constants delta n to the power 5/3. But we need not the total number of energy, we need the density. Right? Therefore,
I'm sorry, I have to go.
Yeah,
I have
that's-
a tea at lunch.
I need to know it, otherwise I need to cut it from the recording. So, we need to add, to multiply and divide by delta V, by the volume. And in order to keep everything correctly, we need to introduce here delta V into the power 3/5. Good? Also possible. Then we redefine anything which is in front as a new constant. And we do have that the total energy in one cell is constant times here we have delta n over delta v times rho to the power 5/3. Good? So one box. And if you have more than one box, if you integrate over all boxes, then the E capital equals summation over all boxes. Which means integral over all 3 dimensions. Rho of r to the power 5/3 G3r. So this is where we were starting.
I think the time is over also.
Well, the time is over for broadcasting. Do you have a minute to wrap it up? So the total number of the total energy is expressed in terms of the density. If we integrate it over the whole space, we are getting the total energy, and we establish a connection between density of electrons and total energy. So if our universe would have no ions, and if electrons would be so silly that they would forget about to interact with each other, we would have theory of everything. Now we need to just bring 2 things back: interaction of electrons to ions and interaction of electrons to each other. Interestingly, that it depends only on the first power of density. It's not not first power, only on density. There are no gradients of density. There are no density in different points. So it depends only locally on density evaluated at one point of space, local. Therefore, this Thomas Fermi theory serves as a first step to so-called local density approximation. See you Wednesday, tomorrow, 5 p.m.